All right, so second derivative test, let's see what it says. And it has a name on it, it has theorem 5. Obviously, I took it from some textbook. Let's delete that. We're not keeping tabs of how many theorems we already know. It says if the derivative is 0 and the second derivative is negative, then f has a local maximum at x equals c. Well, yeah, think about what that means. That means I have a horizontal tangent on f, horizontal tangent on f, and second derivative being less than 0, that means the second derivative is negative. What does this mean, Godinez, on terms of f? It means that f is what?
F is decreasing. Oh no, wait. Concave down.
That's right, concave down. So think about it. If you're concave down, and you can't see the shape of my fist that I'm making, but I'm doing a concave down type of shape. If you're concave down and you have a horizontal tangent, it has to be a maximum. See? If you're concave up and you have a horizontal tangent, it has to be a minimum. Do you guys visually see that? So how does it look visually? Okay, look, here it is. This is f. This is f. And here's f prime being 0. And look, f prime prime is negative. That's concave down. So notice f has a max. See? Concave up, point horizontal tangent. Second derivative is positive, so that means concave up. Notice f has a min. Does that make sense to everyone, guys?
Wait, I'm sorry. Can we review why the second derivative is like positive or negative?
If the second derivative is positive, why you have concave up? Because your rate of change are increasing. The rate of change is increasing, meaning like, look, so notice that your tangent slopes are getting more and more positive. See, so they were at -9, -5, -1, 0, 3, 5. So your f prime is increasing. So that's what it means for the second derivative to be positive. And that happens all the time. If the second derivative is positive, your f is concave up. If the second derivative, sorry, go ahead.
So like as a whole, the second derivative is positive, not just like one section of it.
No, if your second derivative, well, you're always going to be concave up and concave down with an open interval. But we're talking about a very specific value. We're talking about where we have a horizontal tangent.
Oh, okay. Got it.
So if we have a horizontal tangent at a location, and it doesn't have to look like a parabola, guys. It could look something like this. So look. I don't like the way that looks. Well, it's going to be a peak because obviously it's a max or a min, so it doesn't have to necessarily look like a parabola. And we'll try that out with Desmo so you can see. But they're going to have peaks there. Why did I erase that? I didn't want to erase that, but that's fine. Are we okay so far, guys? Okay. So use the second derivative test to find the local extrema. I think extreme. Okay, no big deal. Extreme values of this function. So the first thing we're going to do, guys, is find critical points. Find critical points. Since I have a polynomial, that means I'm going to have horizontal tangents on this one, especially if you have the third-degree polynomial. So here we go. Take a derivative, 3x squared minus 12. I'm going to equal that to 0. I'm going to factor out a 3. So I get 2 points. We could use first derivative test to see whether they're max or mins, but they want us to use the second derivative test. Okay. F prime prime of x equals 6x. F prime prime of 2 equals 12. F prime prime of -2 equals -12. You ready, Godinez?
Yeah.
All right, check it out. Because the second derivative is positive, I know that I am concave up at x equals 2. Does that make sense to everyone? But notice at x equals 2, I also have a horizontal tangent. Do you guys see that? At these values, f has a horizontal tangent. F has a horizontal tangent. Because of that, here we go. So let's think about it. All right, Via, kind of think about it. If you're concave up and my derivative is 0, do I have a max or a min? A min. So I'm going to say it like this. At x equals 2, x, at x equals 2, comma, f has a minimum since f prime of 2 equals 0. You need both conditions. And f prime prime of 2 is positive. You need both conditions, guys.
Wait, I thought. Oh wait, never mind.
You
Yeah,
must have both conditions for it to be a minimum. Okay. No, I have to yawn too, but when I do math, I don't yawn. All right, guys. What about a negative 2? At x equals negative 2. All right. So Mazuka, tell me something about a negative 2. What do I have?
You also have a horizontal tangent.
I have a horizontal tangent, and because the second derivative is negative, I know that at that exact moment, I am concave what?
Down.
Concave down. So because you're concave down, at negative 2, you have a what?
A max.
A max. And you need both conditions, guys. So I'm going to put at x equals negative 2, comma, f, notice that I'm being very specific, has a max since f prime of negative 2 equals 0. That indicates horizontal tangent. And f prime prime of negative 2 is negative. Does that make sense, guys?
Yes.
All right.
Yes,
And let's check.
but
I'm going to use Desmos to check to see if that's true, guys. Let's check. Desmos. Where you at, Desmos? So here's Desmos. I already forgot my function. Lame. What was it, guys? No, the original. X cubed? I thought it was 3x. Okay. X cubed. Minus 12. Yeah. Minus 5. All right. And then I got a point at negative 2. So I'm going to say x. I don't have to say anything. I'm just going to zoom out. And then check it out. Look at that, guys. At negative 2, that definitely is a max. Notice that I'm concave down and I have a horizontal tangent there. Yay, the math works. And notice that at 2, there I am down here. Notice that at 2, you're concave up and you definitely have a min. It works, right? Cool, guys. Very cool. Let's go back. And that is the second derivative test, guys. So now we got some questions here and let's see if we can answer them. So it says you try, so we're going to give you guys a head start for number 1. So number 1, true or false? If the second derivative is 0, then that coordinate is a point of inflection. Justify your answer. So take 30 seconds, answer on the DM, and I'll tell you whether you're right or not. doing that, I'll turn these. You guys want me to turn these? All right, guys, true or false? I don't see any. Oh, I see 3 people have answered. Only 3 of you have answered, guys. Tisk, tisk, tisk. Yeah, kind of. What do you think? Tiff, what do you think? You say true? All right. You're correct, Ochoa. It's false. Yeah. Let me show you one where the derivative, where the second derivative is 0 and it's not a point of inflection. Remember, the second derivative, this is just, what if it doesn't exist? Like, we just need to have a sign change. If it's a polynomial, yeah, you can equal it to 0. So think about x to the 4th. Does everyone agree that x to the 4th is always concave up? Do you guys, you don't know how x to the 4th looks like? It looks like x squared. Yeah. Okay. Don't worry, Viacana. We'll get everyone here. X to an even power, they all look the same. So x squared, x to the 4th, x to the 6th, x to the 8th. The only difference is it's getting skinnier and skinnier, but they all look the same. Yes, it's super skinny, but yes. So look at this one, guys. My derivative, my first one, 4x cubed. The second derivative, 12x squared. Well, look, it equals 0. It equals 0 at 0, but x to the 4th still looks like this. So just because it equals, the second derivative equals 0 doesn't mean it's a point of inflection. It's a possible point of inflection. False. Just like for critical numbers, guys. Remember when we said are all critical numbers max and mins? They're possible max and mins. It's the same thing with the second derivative. What's up, miss?
Wait, a point of inflection, is that where like the derivative changes signs or just
The second
Origin.
derivative, where the second derivative changes signs.
oh, wait. Then if it had said if f prime of c equals 0 is a point of inflection, would it be when the first derivative changes signs?
No, when the first derivative changes signs, that's when you have a max or a min on f, because you just went from positive slopes to negative slopes. So you went from an increasing function to a decreasing function. So if the first derivative changes signs, that's either going to be a max or a min.
So then when the second derivative changes signs, it's a point of inflection, but what does that mean?
It means that you are changing from concave up to concave down, or concave down to concave up.
Oh, okay.
Made me look like a guy.
Because when the second derivative changes, remember the second derivative is positive, you're concave up. If the second derivative is negative, you're concave down. So if you're changing from concave up to concave down, that's my point of inflection. Yeah. A point of inflection looks like, point of inflection is this guy right there. I'm concave down. I'm concave up. And the way I drew this one, yeah, this one is going to pass through second derivative 0. But there it is, concave down to concave up. That's a point of inflection, this dot. That makes sense?
Yes, thank you.
All right, you guys ready for the next one? If the derivative, the first derivative is 0, and the second derivative is negative, then f has a local maximum. We just talked about that. Look at your notes. Take 30 seconds, guys, and I want everyone to answer this one. Good job. We're getting this one right. What do you guys think? Vegana tip? Yeah, true. This is exactly what we just talked about. This is, what do we call this?
The horizontal tangent.
Well, yeah, the f prime of z c equals 0, and then the second derivative is negative. But there's a test. Perfect. This is called the second derivative test. Second derivative test. In case you read that in a literature book, do your second derivative test, and that's what this is. What's the question? True, because second derivative test. That's my justification. Cool or not cool, guys? All right. Here we go. We have a polynomial. It wants to know points of inflection on this graph. We don't have a calculator. I mean, I guess we could get one, but do it without a calculator. All right, take a minute. See if you guys can figure this one out. Check check to see if they made sign changes, Ms. Godinez.
Ouch, that means it's wrong.
No, stop. That does not mean any of that. We're all in this together, miss. Birds of a feather fly together.
Oh, because it's possible, right?
They're
Is that
possible candidates.
Oh, okay.
All right, guys, if you're almost there, here we go. Just keep going if you're almost there. First derivative, 5x to the fourth minus 20x cubed plus 3. I'm going to take one more derivative. Y prime prime equals 20x to the third minus 60x squared. I can factor out a 20x squared. I'm going to have x minus 3. I'm going to equal that to 0 for possible candidates. I get a value of 0 and a value of 3. Now, just because we get 0 and 3 doesn't mean the answer is D, guys. So here we go. I draw a number line. I put 0. I put 3. I call this y prime prime. Or call it whatever, but make sure you label it. Second derivative or something. And then I'm going to insert it back into this equation right here. Remember that 20x squared is always positive. So if I choose like a -5, well, what I circled is always positive. -5 minus 3 is negative. Positive times a negative, negative. If I choose a 1, positive times 1 minus 3, that's a negative. Positive times a negative, negative. If I choose a 5, let's see. Positive times 5 minus 3 is a positive. Positive times a positive, positive. There's only one. There looks like it's a point of inflection at x equals 3. And there it is. And let's test it. Let's see if it really is. So I'm going to go to Desmos.
Wait, so then what's happening at 0? Why would you get that if it's not an actual thing?
Oh, it's not a point of inflection. That's all it means. That means your rate of change is 0 at that moment, and then it just proceeds to continue.
Okay, I got you.
And Desmos, we can look at it just right now. And I already forgot what the equation was. Short-term memory. Y equals Viacana, can you hook me up? Oh. Man, that was not nice, miss. X to the fifth. Minus 5. X to the fourth. Plus 3x. Plus 7. All right, let's see. I'm gonna have to really, oh man, how do we really see this? Look at that. I can see that it's concave down, and then right at x equals 2, 1, 2. Yeah, 2's like right there. And it looks like, well, actually 2's more over here. Right there, I'm supposed to be having a point of inflection at 235, at 2, comma negative 35. Now, I can see that, but with this type of graph, it's going to be kind of hard. Like I see concave down and then concave up.
Wait, Chop, the numbers were 0 and 3.
Oh, 0 and 3. Oh, with a 3, huh?
Wait, what's it 2? I'm so
Well,
confused.
it's because I can't tell with the graph because it's so narrow. Yeah, I guess it's still. Look, see how narrow it is? I'm trying to make it where I can see everything. Let me fix my window. Let me see if I can. Graph settings. I want to look from -5 to -5. Hold on, guys. I want to see this to 10. And then I want to see. Okay, so that looks pretty good right there. And then I want to see from how low does it go? -40. All right, there we go. Now it looks beautiful. To 5. All right, perfect. Now it looks beautiful, guys. So check it out. Let me move it down a little bit. It definitely looks concave down. Look, I was saying 2. What a dummy. At 2, it's still concave down. It definitely looks concave down, and it said that we got it at 3. And check it out. Right at 3, it does look like it's changing concavity from concave down to concave up. Do you guys see that? Look how beautiful this graph looks. And we had a nasty graph right now. And all we have to do is click on settings. And now look, we get this beautiful graph. And now we can't, and you can see, look what happens at 0. Nothing. It's still concave down. I mean, it looks like the rate of change is flattening, but then it still continues and it's still concave down. Isn't that kind of cool, Godinez?
Super cool.
I think so too. How do we feel, guys? Don't cry, Miss Tiff. Oh, okay.